In the previous module, we had tried to get the scales of delta t, Nusselt number, velocity and delta for larger Prandtl fluids, that is high Prandtl number fluids. Just to recall what we had done, so we had, this is the inertia, this is the friction, this is the buoyancy. So for high Prandtl number fluids, we said that delta t layer is ruled by the friction to buoyancy balance. Friction to buoyancy balance, because for high Prandtl number fluids, nu is very large, so the friction is large, so friction is balanced by buoyancy. For low Prandtl number fluids, delta t layer is governed by inertia to buoyancy, and nu is very less, so nu is less, so that's why we say we take inertia as high. Inertia is balanced by buoyancy. So these are the typical values for various Prandtl number fluids. Now for high Prandtl fluids, so what we took, friction balanced by buoyancy, that reduces to delta t is of the order of h Rayleigh to the power of minus 1 by 4. Nusselt number is of the order of delta t by h to the power of minus 1. So Nusselt number is of the order of Rayleigh to the power of 1 by 4. And V is of the order of alpha h by delta t squared. So if I substitute for delta t squared, I get V is of the order of alpha by h Rayleigh to the power of 1 by 2. So these results are confirmed through experiments and through similarity solutions and integral approach. Now if we try to plot delta t for high Prandtl fluids, delta t, this is the delta t, and this extends to range of delta t, small delta t, that is the driving layer where friction is balanced by the buoyancy. Within this layer, my velocity is picked up and it has reached the peak velocity v, and now beyond this delta t there is no buoyancy. So the inertia force has to be balanced by friction before the velocity is brought to 0. So the velocity is brought to 0 in the driven unheated layer where the friction is balanced by inertia. So now we need to find what is this delta. So we found that delta, we took the inertia force, the friction force and the buoyancy force. So what did we do? We took the scale of the u as u, x as delta, not delta t. Please notice that this is delta. So del v by y, delta y, that is v by h. So we get u is of the order of v delta by h, and v we have already found alpha by h Rayleigh to the power of half. So now in this unheated layer, inertia is balanced by friction, because of which I get v squared by h. See here, v delta by h, v by delta comma v and v by h, nu v by delta squared. So you get v squared by h nu v by delta squared. So that is delta squared by h nu by v. So if I multiply both sides by h in the denominator, I get delta squared by h squared. This is of the order of nu by vh, and if I substitute for v, I get delta by h as Prandtl to the power of half Rayleigh to the power of minus 1 by 4. See, minus Rayleigh to the power of minus 1 by 4 because it is decreasing, because there is no temperature difference. So delta is of the order of Prandtl to the power of half and Rayleigh to the power of minus 1 by 4. So now if you take delta by delta t, it is of the order of Prandtl to the power of half. So we have found all the scales of delta t, delta, Nusselt number, v, and appreciated the fact that delta is greater than delta t. So now let us take up low Prandtl fluids. Low Prandtl fluids. Low Prandtl fluids. So here we said that delta t is ruled by the balance between inertia to buoyancy. That is, we know that we have written h by delta t to the power of 4, Prandtl to the power of minus 1, Rayleigh to the power of minus 1, comma, h by delta t to the power of 4, Rayleigh to the power of minus 1, comma 1. This was inertia, this is friction, this is buoyancy. Now we are saying that inertia is balanced by buoyancy. If that is true, inertia is h by delta t to the power of 4, Prandtl to the power of minus 1, Rayleigh number to the power of minus 1 is of the order of 1. So, you get delta t is of the order of h Rayleigh into Prandtl to the power of minus 1 by 4. Notice in my earlier for delta t Prandtl was not there, here we have Prandtl. If you notice for high Prandtl number delta t was just h Rayleigh to the power of minus 1 by 4, but here you have Prandtl number. Why? Because Prandtl number is very less, thermal boundary layer thickness has to come down. So, Nusselt number, I do not have to do again, we have found just now that delta t by h to the power of minus 1. If you recall, what I had written here is h by k, k by ts minus t infinity or t f into delta t by del x, del t by del x into h by k is of the order of 1 by ts minus tf into ts minus tf upon delta t is the scale h. So, it is h by delta t. So, Nusselt number is the scales to delta t by h to the power of minus 1. So, you have Nusselt number is of the order of Rayleigh into Prandtl to the power of 1 by 4. So, that is Nusselt number. Okay. Now, what is the scale of V? V is alpha h upon delta t squared, that is alpha h delta t squared is h squared Rayleigh to the power of minus half Prandtl to the power of minus half, that is 1 by 4 into 2. So, you get minus half. So, that is alpha by h. So, V is of the order of alpha by h Rayleigh into Prandtl to the power of half. So, as Rayleigh number increases, my velocity increases. So, these are the three scales which we have gotten for low Prandtl fluids. So, these results again, as I say, are confirmed through experiments and closed form solutions. Now, let us see how can we plot the temperature, and the velocity. So, let us plot. This is vertical is either delta t or velocity, and this is x. Now, inertia, we started with inertia to buoyancy. So, as long as buoyancy is there, that long inertia is there. So, you have the temperature gradient as something like this. So, this is the heated layer, that is where in which you have whole of this. Here you have inertia balanced by buoyancy. This is Prandtl number less than 1, and this vertical axis is my delta t, and this is the domain delta t. Now, what happens is the velocity. Now, let us go to the slides. So, if you have to understand little bit some theory. So, the delta t is driven upward by buoyancy and restrained by inertia. This means outside the layer, the fluid is isothermal, that is outside this layer, the fluid is isothermal, that is here. The fluid is isothermal, the PPT, we are in PPT, where the fluid is isothermal and the buoyancy is absent. So, the fluid is motionless. So, the fluid is motionless. The motionless means, what does it mean? That means it cannot have any velocity there. So, the velocity profile must then be as wide as the temperature profile. It cannot go beyond this because there is no inertia beyond that. So, however, since there is a no slip condition, still applies at the wall. So there is a location of the peak velocity. That means there is a velocity which it will pick up and then it will reduce to 0 within delta t. So this location of the peak velocity, let us call that as delta v. So now the velocity profile must be as wide as the temperature profile, and let delta v be the thickness of a very thin layer right near the wall, a layer in which the buoyancy driven fluid, what is in this region, this is the velocity, in this region, what is, it has picked up, inertia has picked up, but here it is balanced. So inertia is balanced by friction. Sorry, here in this region, this is the region where friction is balanced by buoyancy. Friction is balanced by buoyancy. Okay, because this is the region. Just let me recall. See, the velocity profile must be as wide as the temperature profile, and delta v be the thickness of a thin layer right near the wall. So a layer, this has picked up, this is picked up here in this domain, it has picked up velocity by virtue of buoyancy. So that is the reason. So in this region, so the buoyancy, and there is a lot of friction, so the buoyancy has to work against that friction. So that is the reason buoyancy is balanced by the friction. So to get our velocity, let us work. This is low Prandtl fluids. Low Prandtl fluids. Buoyancy has to be balanced by friction. So what is my equation? U del v by del x plus v del v by del y equal to nu del squared v by del x squared plus g beta t minus t infinity. Recall that this is inertia, this is friction, this is buoyancy. It will be little difficult to at the first sight to understand that the buoyancy is balanced by friction, but near wall it is the friction which is dominant and the buoyancy is driving. That is the reason buoyancy is balancing friction and inertia is neglected. So buoyancy is balanced by friction. So what is buoyancy? G beta delta t is balanced by friction, that is nu scale of v, x is delta v squared. Okay, so I know v already. What is my v? V is of the order of alpha by h. We had just now found v is of the order of alpha by h Rayleigh Prandtl to the power of half. Okay, so I get, if I substitute this, so I get delta v squared is of the order of nu v by g beta delta t. I have not substituted yet v. If I substitute v, delta v squared nu upon g beta delta t, v is alpha by h Rayleigh into Prandtl to the power of half. Okay, so now what do I do here? So you recall Rayleigh number is g beta delta t h cube upon alpha nu. Okay, so if you multiply both sides, left hand side and right hand side, by h squared, delta v squared upon h squared is of the order of nu alpha upon g beta delta t h cube into Rayleigh to the power of half, Prandtl to the power of half. So what do I get? I get delta V by H whole squared is of the order of 1 upon Rayleigh into Rayleigh to the power of half into Prandtl to the power of half. That is, I get Prandtl upon Rayleigh to the power of half. I need to introduce one number called Grashof number now. So far I had not introduced. That is, Grashof number equal to Rayleigh number upon Prandtl number. What is Rayleigh number? G beta delta T H cube upon alpha nu. Prandtl is nu by alpha, that is G beta delta T H cube upon nu squared is my Grashof number. So, delta V by H squared is of the order of Rayleigh by Prandtl will become Grashof number. So, you have Grashof number to the power of half. So, delta V is of the order of H Grashof number to the power of, this is actually minus 1 by 4. Always for boundary layer thickness, Grashof or Rayleigh number should be having power negative because it is resistance. So, it is intuitive. So, now if I find delta V by delta T is of the order of, what is delta V? H GRH to the power of minus 1 by 4 upon delta T. Delta T is, if you just recall, H RAH PR to the power of minus 1 by 4. So, you get H RAH PR to the power of minus 1 by 4. So, you get GR to the power of minus 1 by 4 upon Rayleigh number can be written as Grashof into Prandtl. This is Rayleigh into already existing Prandtl was there. So, you have minus 1 by 4. So, you get GR to the power of minus 1 by 4, GR to the power of minus 1 by 4 will get cancelled out. So, you get Prandtl squared to the power of minus 1 by 4, that is Prandtl to the power of half. So, delta V by delta T is of the order of Prandtl to the power of half. Okay. So, this is what, so here I have, let us just summarize all that what we have studied so far, so that we get a feel of what we have done. Let us write that, let us write various parameters, that is Prandtl number greater than 1 and Prandtl number less than 1. Thermal boundary layer thickness, that is delta T. So, we have found delta T as H RAH to the power of minus 1 by 4. Now, here delta T is of the order of Prandtl to the power of minus 1 by 4 into H RAH to the power of minus 1 by 4. Please notice this difference. To notice this difference only I am rewriting again. Okay. So, then distance from the wall, to velocity peak. If you just recall, you see this was for high Prandtl fluids and this is for low Prandtl fluids. What we are asking is distance until which the velocity is peak, that is delta T. So, for high Prandtl fluids it will be delta T and for low Prandtl fluids it will be delta V. So, delta T we have already found, that is delta V. Delta V is of the order of delta T, which is H RAH to the power of minus 1 by 4, and here delta V just now we have found, that is Prandtl to the power of 1 by 4 H RAH to the power of minus 1 by 4. This is what we just found. So, then thickness of the wall jet. Thickness of wall jet. What is thickness of wall jet? Thickness of the wall jet is nothing but delta, that is how long my velocity exists. How long wall jet, where does wall jet means how long the jet exists, how long the velocity exists, that is delta. Delta we have found that as PR to the power of half H RAH to the power of minus 1 by 4. And here for low Prandtl fluids, delta exists as long as delta T exists. So it will be of the order of delta T, that is Prandtl to the power of minus 1 by 4 H RAH to the power of minus 1 by 4. Now next is velocity scale. The velocity scale is V is of the order of alpha by H Rayleigh to the power of half, and here V is of the order of alpha by H RAH PR to the power of 1 by 2. So notice there is Prandtl number. The last but not the least is the Nusselt number. This is the most important heat transfer parameter for calculating the heat transfer rate. As an engineer, we are interested in Nusselt number only. So the Nusselt number is of the order of Rayleigh number to the power of 1 by 4. And Nusselt number is of the order of Rayleigh to the power of 1 by 4 and Prandtl to the power of 1 by 4. You see here, it's very important. See, Nusselt number, that is the heat transfer coefficient, goes on increasing with the increase of the Rayleigh number. Recall, Rayleigh number is nothing but G beta delta T H cube by alpha nu. So as delta T goes on increasing, so my Nusselt number goes on increasing. Okay, this is the fundamental difference between the forced convection and the natural convection. In the forced convection, the heat transfer coefficient is not at all dependent, is not a function of delta T or Q double dash. But here Nusselt number, here in the natural convection, H is dependent on delta T. This is the fundamental difference between the forced convection. This is in case of, for forced convection only, H is not a function of delta T and Q double dash. Okay, so when you do the experiments, your H should get, whatever be your Q double dash, delta T should get adjusted so that you get the same H. But here your H will increase with the increase of the delta T. So, and now you see Nusselt number decreases with the decrease of Prandtl number for a given Rayleigh number for low Prandtl fluids. And here it is for high Prandtl fluids, it is independent of the Prandtl number. So this is the fundamental thing which we are getting from this scale analysis. So now let me just recall all the non-dimensional numbers. So let us just say all non-dimensional numbers. Once again, let us write. I am going to do scale analysis and come up with these non-dimensional numbers. But before I do that, I have to write this. GRH equal to G beta Ts minus T infinity H cube upon nu squared. Nu is kinematic viscosity, G is acceleration due to gravity, beta is coefficient of thermal expansion, Ts minus T infinity, Ts is the surface temperature, T infinity is the fluid temperature in the atmosphere, H is the height of the plate, REH is U infinity H by nu. Rayleigh number is equal to G beta Ts minus T infinity H cube upon alpha nu, and Prandtl number equal to nu upon alpha, and Rayleigh number is equal to Grashof number into Prandtl number. So these are the non-dimensional numbers which we have gotten from our analysis. Now let us take up, what we shall do is, conventionally what we do, similarity approach. We do similarity approach. We do similarity approach. That is, what are my equations? Del u by del x plus del v by del y equal to 0. U boundary layer equation only I am taking. U del v by del x plus v del v by del y equal to nu del squared v by del x squared plus g beta t minus t infinity. U del t by del x plus v del t by del y, my energy equation, alpha del square t by del x squared plus del square t by del y squared. Of course, I can neglect this, actually this term can be neglected. So what do I do for similarity approach is that x star, that is x I non-dimensionalize with h, y star y I non-dimensionalize with h, u star u I non-dimensionalize with u infinity, v star I non-dimensionalize v by u infinity, and t star is t minus t infinity upon ts minus t infinity. See, unlike forced convection, I will not be knowing the u infinity in the natural convection. U infinity can be visualized as a characteristic velocity, maybe the peak velocity in our graphs what we saw earlier. So, but we will not get directly. We will not get directly unlike forced convection. What we really know is the delta t, that is ts minus t infinity. So, with this we will stop this module, and in this next module we will do this non-dimensionalization and get the non-dimensional numbers in the subsequent module. So, that is the plan for the next module. Thank you.